Salutations, Internet. Good time zone. Let's start out with the housekeeping. Housekeeping and review. So, we last episode derived our shiny new orbital element equations for the Keplerian elements. If you want to see how we did that, go check out last week's video. The only other housekeeping item that I am aware of would be the equation sheet in the video descriptions. I do still want to do that. I haven't yet because of a number of reasons. One is that I still have a full-time job, and recording, editing, and doing all the work for these videos takes up a fair amount of time, so I haven't invested much time yet into figuring out how to do that. The other reason is, well, I'm new to YouTube, as it turns out. So, there's still a lot of stuff that I'm learning and figuring out. Thank you for your patience while I'm going through it. This will be the last time that I explicitly mention the equation sheet, but I do intend to go back through all of the videos and put in the equation sheet, the completed equation sheet, into each video, and from there you can download it. It'll be yours. If you want to know how we derived the equations, what each of the symbols means, then you're just gonna have to watch the videos. And I think that's a fair trade. In any event, let's get into our video of the day. So we have a lot of the physical properties. We have a lot of the geometric properties of our orbit. So we have like an angular momentum, a radius, a size and a shape, velocity, and a periodicity. And I'm going to use that last one as a segue into today's video, because what if we wanted to know how long our satellite spends in a certain region? For example, if we had a satellite that wanted to look at what exactly is happening in the Van Allen belts, and I might do a whole thing about that later, but we don't want to spend all our time there, okay, we design an orbit based off of those criteria. How do we determine how much time that satellite spends up there? If I bring it back to the examples that we've been working with in this series, if we want to know how much time the satellite spends above the 20,000 kilometer radius mark, well, it's not so easy as to say, well, half of the time it spends up there. No, not really, because it's moving slower at that distance, because our velocity is based off of our radius, and our radius is based off of our angle. And if you're not careful, you can get an infinite feedback loop between the two of them, where your velocity is related to your radius is related to your velocity. It's a whole mess. So it's not so easy as this. I wish it were, but it's not. So instead, we are going to turn to the works of people who are a little bit smarter than me, or a lot bit smarter than me, and they have worked it out. So let's take a look at what they've determined. So we'll start with the ellipse here. So all of the chunk, the ellipse that's sitting in the box there. And we can see that, okay, so we have our host body at a focal point, we have a radius, we have an angle with the eccentricity vector, and that's all stuff that we are familiar with. What we are not familiar with is going to be what this circle is. This is called an auxiliary circle. And this is basically a circle that is, oh, I forgot the term for it. I think it's circumscribed. It's circumscribed around our orbit. So it touches the periaps and the apoaps. And so let me write it this way because I realize I have two A's on here. It touches our periaps and our apoaps, and it is centered at point O, which is also the center point of our orbit. The radius for the circle is the semi-major axis. Shouldn't be a surprise to anyone. And what we are doing here is, so we have our little triangle in here. Have our little triangle of the radius and theta and the satellite. And what happens is we take our eccentricity vector and we project straight up through our satellite and project to point Q here on our auxiliary circle. And we draw a line from the origin here, from O to Q of radius A, and we use the angle E, which is the eccentric anomaly angle. And that is going to be the start. That's going to be the basis of our equations moving forward. Similarly, over here, I just took the triangles that we had in here, and I moved them over to here. So these are geometrically the same triangles. They just lack the context of our auxiliary circle. No big deal. So if we have the Earth here at the focal point, and we have the center of the orbit at point O here, then we can do, let's do this. We can do this. So if we project our radius straight down, that is going to give us an equation of the radius times the cosine of our true anomaly angle. This, the distance from the center to a focal point of an ellipse, geometrically speaking, that is going to be our semi-major axis times our eccentricity. And the two of them combined is going to be equal to the semi-major axis projected down. So A times the cosine of our eccentric anomaly angle. And you would not believe how many takes I had to do in order to realize that I was accidentally writing the arc cosine of the eccentric anomaly angle. Don't do that. That's wrong. Learn from my mistakes. All right. So now we can combine these together. So let's write it up this way. We have A times E, the small e, plus R cosine of theta is equal to A times the cosine of big E. Yes, this will probably get confusing as we go on. Not to worry, we can figure it out. So, let's take a moment to have a side note in here. I do not like having a trig term for theta and a trig term for E. I want to have just one of those angles, if it's at all possible. We're going to do this in a bit of a roundabout way. So let's hop back over to here. No, before we do that, I see that we have an A, a semi-major axis, an eccentricity, another semi-major axis. I think we can take our radius and we can redefine it. So if we take this equation, but instead of h squared by mu, we have h squared by mu here is equal to a times 1 minus eccentricity squared. So if we put all that together, yes, I'm going to give you a warning now. The equations will get a little messy. So we have r is equal to a times 1 minus the eccentricity squared over 1 plus the eccentricity times the cosine of theta. And on the surface, it doesn't really look like we've solved the problem. We've just introduced another cosine of theta here. Except it would be nicer to have it be explicitly e. Yeah, let's not worry about that. Let's bring the denominator over to the other side here. And I'll go ahead and I'll distribute everything. We have r plus r times e times the cosine of theta is equal to a minus a times e squared. And some of you may be making some connections as to why we're going down this route, but let me take another step here before I point it out. So let's bring this over to the left and we'll throw this over to the right. So we have AE squared plus RE cosine of theta is equal to A minus R. All right. And now you may be able to see why we went down this route. If we go over here to do this, if we scale this entire equation by the eccentricity, it doesn't matter what we scale it by because it will be equal to itself. You're just scaling the same thing. It's fine. But if we scale it by E, then we have this side being equal to this side, which means that we can have let me bring it over here. A minus R is equal to A E cosine of the eccentric anomaly angle. And when we solve for R, when we solve for radius, we get our semi-major axis times 1 minus the eccentricity times cosine of the eccentric anomaly angle. Give me a second. Because I double negative myself, I psych myself out. Yes, that is it exactly. And that is something that we can box. Because now we have radius in terms of our eccentric anomaly angle, which is very useful for us. Now, we're not nearly done yet. So we are looking for a time element. We want to know how long it takes for something to occur. When I think of time elements, the first thing I think of is a time derivative. So it is not a bad place to start. So if we were to do this, take the time derivative of both sides, then we have r dot is equal to A is not changing in time. So R changes in time. So yeah, we can have that be R dot. A does not change with time, but it's a coefficient. So we'll slap that out here. 1 is a constant. That goes to 0. I'll leave some space times E. All right. I have to do this every single time. Don't mind me. So we have cosine over down here. We have sine up here. When theta is 0, then our cosine is 1 and our sine is 0. When theta increases, sine increases by the rate of theta, so by the rate of cosine. So cosine is the rate of change of sine. Cosine is the rate of change of sine. So minus sine is the rate of change of cosine. So we want, let me write down sine before I forget. And then I'll put the minus up here. The E, the eccentric anomaly angle, will change with time. We can have that be E dot. The negatives will cancel out, and when you write it a little neater, you'll have E dot sine of the eccentric anomaly angle. All right. So as it would happen, this R, we are looking at the scalar R dot, not the vector R dot. This is our radial velocity. This is VR. And just to really remind myself later, is that our VR equation is here, mu by h times e sine of theta. Mu by h times e times the sine of theta. So that makes these two equivalent to one another, right? So let's see if we do, let's do it this way. E dot sine of E is equal to mu E sine of theta all divided by h. And I am going to mark this with a star just so I don't lose it later, because we're gonna do some doctoring up of this equation. Again, we have two different trig functions, one by e, one by theta, and we don't like that. So let's do our best to try and fix that. Let's start by focusing on our angular momentum, because we have a's, e's, mu's, and then we have this h, and that h can be expressed in terms of, let me find it. There it is. In terms of mu's, a's, and e's. Despite having written this, I will still lose my equations. It's fine. So h is equal to the square root of mu a 1 minus e squared. I'm taking up a lot of space with my writing. Let me try and condense that down. All right, when you plug it in, when you plug your angular momentum into this, oh boy, you're gonna get a bunch of dots. You're gonna get e dot times the sine of the eccentric anomaly angle is equal to mu times e times sine of theta over the square root of mu times a times 1 minus e squared. And I apologize. This is actually the one that I want to keep track of. That is actually the important one. I'm just gonna mark. That's more so for me. I'm just gonna mark that out for me so that I don't look at that later and go, why did I decide to do it this way? All right. So we are looking at the sign of a value here. If we go back up to the diagram I have here, that is the vertical component. So the vertical component of this triangle. This, so if we have A times the sine of the eccentric anomaly angle, that is going to be proportional to, that has to be proportional to r times the sine of theta. And as it turns out, so at full value, when the eccentric anomaly angle is equal to 90, so we are going straight up, we have a circle still of radius a, but now we look at the semi-minor axis of our ellipse, and that is actually the ratio that we use. That is a geometric property. And as a reminder, our semi-minor axis is just equal to the semi-major axis times the square root of 1 minus the eccentricity squared. Which means that both semi-major axes will cancel out, and it is really... actually, I'll just write it down here, because I'm going to need to here in a little bit anyway. That will end up being... so... Actually, let me not lose track. So that will be a sine of the eccentric anomaly angle being equal to the radius, as I had it written up here, the radius times the sine of theta divided by the square root of 1 minus the eccentricity squared. And, well, once again, it'd be nice to have things in terms of E, because theta isn't all that helpful in determining time. So we have our R, the R equation that we just solved for, this one right here, that can replace the R down here, which turns into, let's remember to do this. Sine of E is equal to A times 1 minus the eccentricity times the cosine. Let me write that a little bit neater. The cosine, COS, make that actually look like a C. The cosine of not theta, but the eccentric anomaly angle. And that be multiplied by the sine of theta, all divided by the square root of 1 minus E squared. All right, so let's solve for sine now. We still have the problem of, we have two different angles that we're trying to solve, but we can put one in relation to the other. Since we have sine over here, we'll put the sine of theta is equal to the square root of 1. Actually, no. Let's do it this way. A times the square root of 1 minus e squared times the sine of our eccentric anomaly angle all over A times 1 minus the eccentricity times the cosine of the eccentric anomaly angle. The a's will cancel out. That's very handy. And so when we plug this back into this equation up here, I won't be able to fit all of that on. Darn. Oh well. So we have AE dot times the sine, the eccentricity is equal to the mu over the square root of mu times a, and then I will separate out the square root of 1 minus e squared, just to make it easier on me, times the sine of theta, which we have written as the square root of 1 minus the eccentricity squared, sine of e, all over 1 minus e cosine of big E. So some things will cancel out now. We can cancel out that, and we can cancel out this. Then we can solve for E dot. So if we do that, we have E dot is equal to, give me some more room. My handwriting is still massive today. And messy. Let me try that again. E dot is equal to, so we have 1 whole mu divided by the square root of mu. That's the square root of mu in the numerator. And a to 3 halves. Okay. So mu by a cubed, square rooted, times 1 over 1 minus e cosine of big E. And this is, so E dot is the E dt. That is the rate of change of the eccentric anomaly angle with respect to time. So if we want to solve for time, let's put all of this over on this side, and then we can put our dt up here. And that is going to look like dt is equal to the square root of a cubed divided by mu times 1 minus e cosine of big E dE. And so we integrate these, and we can use any range that we want for integrating these. I would recommend doing something that is simple. So what is simple is probably using one of our reference points as the periapse. So what that looks like in this context is our final t minus our periapse t, which this we can define as 0 for future calculations. have that be equal to the, let's see, this is a constant that can be taken out. A cubed by mu square rooted, and dE. Okay, here comes the fun part. We have E minus the eccentricity of big E. So funny story about this. It's wrong. It's wrong. This is what happens when you take a cross between a derivative and an integral. And so while I was doing the integral to get from here to here, I took the variable to the outside, as one does during a derivative. Pro tip, don't do that. Don't do that. That's how you get a wrong equation. So as it turns out, that is the only part of it that is wrong. At least looking at my notes here. Yep, double checking with my notes. That is the only step about it that is wrong. Brownie points to you if you managed to catch that before this edit came in. So I will also do I will do everyone here a favor, and I will just save everyone a little bit of time. I go through a long-winded explanation of how to get from cosine to sine, but I got lost partway through the translation. It's not really that important. I'm just going to condense it down for everyone here. So we have a triangle, we have our theta, and cosine looks at the adjacent leg, and sine looks at the opposite leg. So as theta increases, meaning that it moves in that direction, our sine goes up by the rate of change of the cosine, and our cosine goes down by the rate of change of our sine. So a perhaps better or more accurate way of wording that is that it goes up by the negative of our sine. And so you propagate this forward far enough, then you can get all the derivations, and then you want to look at it in the backwards direction, so you can find out that your minus cosine should get you a minus sine, which is what I did. And there you go. The only mistake I will ever make, and the only explanation that I will ever have to give. While it is nice to be able to understand it well enough and derive it, it's still a huge headache and it takes a fair amount of time. So if anybody has a faster way of doing that, please do leave a comment in this video. Please let me know. Otherwise, you're going to be, you're going to have to be dealing with me trying to figure that out every single time I do a derivative of a trig function. With that note out of the way, we have our time, I guess this is a delta t equation. We have the time from periapse to a particular point. And as a note, you will see that we have two eccentric anomaly angles that are outside of a trig function. This is fine. This just means that we need to use radians. We cannot use degrees or gradients. I have not yet had the pleasure of using gradients, but that's beside the point. We are using radians for these values. This, use radians, use degrees, use whatever you'd like, as long as your calculator knows that you are trying to use it. Doesn't really matter. All right. I think we have enough time for an example, so if you will... No, I just saw the timer. I will save my example for a future video, because this recording has taken about 34 minutes, and I don't know how much that's going to boil down during the editing process. So this is a good stopping point for now. Do keep in mind that there are plenty of other equations that are a result of let's see, let's go back up to here. There are plenty more equations that are a result of using this setup, where we are using an auxiliary circle. So we will be revisiting this in future episodes. Until then, thank you all so much for stopping by.